In this lesson, we're going to tackle L'Hopital's rule, which is a rule that would help us cancel out indeterminate forms of limits in the form 0 over 0 or infinity over infinity. Now, in a previous lesson, we've seen different techniques in order to cancel out indeterminate forms of limit and evaluate these limits. However, this lesson is specific to L'Hopital's rule, which only works if the limit is in the form of the limit when x is approaching any value, doesn't really matter, of a quotient of two differentiable functions that gives a 0 over 0 or an infinity over infinity. So if you have the limit of f over d to be equal to 0 over 0 or infinity over infinity, then this limit is in fact equal to the limit of f prime over g prime at that value of x. So this is L'Hopital's rule. So whenever you end up with 0 over 0 or infinity over infinity, what you could do is, in fact, consider the limit of the quotient where you have the derivative of the numerator divided by the derivative of the denominator. However, if the limit of f prime over g prime also ended up being 0 over 0 or infinity over infinity, you could still apply L'Hopital's rule again over and over. You can apply it indefinitely. Okay, so let's just put this into examples here. So I have the limit when x is approaching 1 of this quotient of two polynomials. So evaluating this function at x equals to 1. So I believe in order for this to work, the 4 and 3 have to be the other way around. So the limit when x is approaching 1 of x squared minus 4x plus 3 over x squared plus 4x minus 5. So having 1 for x, it's 1 minus 4 plus 3, that's a 0. And 1 plus 4 minus 5, that's also a 0. So I have 0 over 0. Usually, since this is a quotient of two polynomials at a finite value, in that case, we could cancel that indetermination by factorizing the numerator and factorizing the denominator and canceling out the common factor. However, since this is 0 over 0, now we have the option to use L'Hopital's rule, which consists of considering the limit when x is approaching 1 of the derivative of the numerator, which is 2x minus 4, over the derivative of the denominator, which is 2x plus 4. Now, replacing 1 for x, it's 2 minus 4, which is a negative 2, and 2 plus 4, which is a 6, which is a negative 1/3. So following L'Hopital's rule, this limit ended up being equals to negative 1/3. In this following example, we have a limit at infinity of a quotient of two polynomials. We have 2x squared plus 1 over x5 minus 2 with a limit at positive infinity. So at positive infinity, the numerator is infinity and the denominator is infinity. So I do have infinity over infinity here, so I could apply L'Hopital's rule. Now, usually whenever we end up with a limit of infinity over infinity with a quotient of two polynomials when x is approaching infinity, in that case, we could cancel out that indetermination by considering the terms of the highest degree since the limit is at infinity. So by considering this equal to the limit of the terms with the highest degree of the quotient of the terms of the highest degree, you would cancel out that indetermination. However, since this is infinity over infinity, we could apply L'Hopital's rule. So that would be the limit when x is approaching positive infinity of 4x over the derivative of the denominator is 5x to the 4th. Now you'd notice that this is also infinity over infinity. So over here, you could go by two ways. You could apply L'Hopital's rule again, or you could notice that the numerator and denominator have x as a common factor, so you could cancel out that common factor. So over here, if I were to cancel out that common factor, I would end up with 4 over 5x cubed if I cancel out x. and that would be 4 over positive infinity, which is 0. However, if I decided to use L'Hopital's rule again, so the limit when x is approaching positive infinity of the derivative of 4x is 4, and the derivative of 5x to the 4 is 20x cubed. So at positive infinity, this is 4 over positive infinity, which is a 0. So you notice either ways, you end up with exactly the same answer. So you could apply L'Hopital's rule again, or you could decide to cancel out the common factor in case you ended up with a common factor following applying L'Hopital's rule the first time. Now over here, the limit when x is approaching 0 of x cosine x minus sine over x minus sine. Now over here, even though the limit is at 0, which is a finite number, however, the quotient I have here does not involve polynomials, so I can't use factorization here. I have no choice but to use L'Hopital's rule here, because this limit ends up being 0 over 0. Since at x equals to 0, cosine x is 1, and 1 times 0 is 0. Sine 0 is 0, so that's 0 at the numerator, and 0 minus 0, so that's 0 at the denominator. Now, in order to apply L'Hopital's rule, what I need to do is find the derivative of the numerator and the derivative of the denominator. Now, at the denominator, I have 1 minus cosine x. The derivative of x is 1, and the derivative of sine is cosine. At the numerator, x times cosine is in the form u times v. So the derivative here is u prime v plus v prime u. So if x is, if u is x, then u prime is 1. And if v is cosine, then v prime is negative sine. So u prime times v, this is cosine x, plus v prime times u, so that's negative x sine x. And I still have one last term here, which is negative sine. So that's a negative, and the derivative of sine is cosine. Now you'd notice that cosine minus cosine cancel out. So that's the limit when x is approaching 0 of negative sine x over 1 minus cosine x. Now applying 0 for x, so at the numerator I still have a 0, and at the denominator I still have a 0 because 1 minus cosine 0, and cosine 0 is 1, so 1 minus 1, that's a 0. So I could apply L'Hopital's rule again. So limit when x is approaching 0 of, at the denominator the derivative of 1 is 0, negative the derivative of cosine, and the derivative of cosine is negative sine, so that's negative into negative sine. That leaves me with sine x. And at the numerator, I have a product again, that's in the form u times v, where u is negative x, and v is sine x. So u prime is negative 1, and v prime is cosine. So u prime v plus v prime u, so that is negative sine minus x times cosine. Okay, at x equals to 0, you'd notice that this gives you again 0 over 0. However, since the denominator consists of exactly one term, instead of keep applying L'Hopital's rule, which you could do, and it could eventually lead you to the answer, over here, what you could do is just split the fraction. So by just splitting the fraction, negative sine over sine is negative 1, and negative x cosine over sine. So over here, negative 1, it has no variables, so its limit is negative 1. There's nothing much I can do to it. However, over here, you notice I have negative x cosine over sine. This is a 0 over 0. You could decide to apply L'Hopital's rule to this quotient only. However, we do have a property that says that the limit when x is approaching 0. Now, I would think of that property because the limit here is approaching 0. So the limit when x is approaching 0 of sine x over x is 1. However, you notice here I have an x over sine. It's okay. X over sine is the reciprocal of sine over x. So all you have to do is just consider the reciprocal of the limit. Now, this property has a geometrical proof, and it could also be justified using L'Hopital's rule. If at the numerator, now using L'Hopital's rule, because sine x over x has a limit of 0 over 0 at x equals to 0. So the derivative of sine is cosine, and the derivative of x is 1, and cosine 0 is 1. So over here, what you could do is just apply that rule. So if the limit of sine x over x is 1, then the limit of x over sine at x equals to 0 is the reciprocal of this limit, and the reciprocal of 1 is in fact 1. So whenever you have a limit at 0 and you have sine over x or x over sine, you could just consider that immediately to be equals to 1. So that leaves me with negative 1 minus cosine x, since this quotient is equals to 1, and cosine 0 is 1. So that leaves me with negative 1 minus 1, which is a negative 2. Now, regarding our last limit here, we have the limit when x is approaching 0 of x times cotan. Now, you'd notice this is not a quotient. However, by applying 0 for x has a limit of 0, and cotan of 0 is infinity. Now, you need to remember the trigonometric lines of remarkable angles. So at 0, cotan is infinity. Now, this is 0 times infinity. However, we've mentioned at the beginning that L'Hopital's rule can only be applied if you have a limit of 0 over 0 or infinity over infinity. However, this is a 0 times infinity. We cannot apply L'Hopital's rule at the function when the function is as is. Okay, so however, when it's 0 times infinity, there is a way to change 0 times infinity to 0 over 0 or infinity over infinity, because we know for a fact that 0 is the reciprocal of infinity and infinity is the reciprocal of 0. So in case, for example, if you have the limit when x is approaching any value, alpha, of a times b is 0 times infinity, where the limit of a is 0 and the limit of b is infinity. Now, how can we change that to 0 over 0 or infinity over infinity? Since 0 and infinity are reciprocals of one another, I could think of considering one of them divided by the reciprocal of the second, which means that this would in fact be equivalent to the limit when x is approaching alpha of a over 1 over b. A over 1 over b is a times b. And in this case, a has a limit of 0, and b having a limit of infinity, 1 over infinity is 0. So in that case, I have changed the limit 0 over 0 and into a quotient, the function into a quotient as well. Or have the limit when x is approaching alpha of, I could consider b divided by 1 over a, which is an infinity over infinity. Since b has a limit of infinity and a having a limit of 0, then 1 over 0 is infinity. So how can we apply that to our given function here, x times cotan? Now, it could be x over 1 over cotan x, or cotan x over 1 over x. Both of these quotients lead back to x times cotan x. However, which one is easier for me to go for? Now, over here, you'd notice that 1 over cotan is in fact tan x, since cotan is the reciprocal function of tan x. So, and I already know the derivative of tan. So for that reason, I might find it easier to go for this first option, because if I went for the second one, then I'd have to, by applying L'Hopital's rule, I'd have to find the derivative of cotan, I'd have to give the derivative of cotan, and then divide by the derivative of 1 over x, which is negative 1 over x squared, so the derivative would still be a quotient. So the first one might seem easier to go for. So that's the limit when x is approaching 0 of x over 1 over cotan, which is tan x. And that is a 0 over 0. So this one leads to 0 over 0. If you went for this one, it would in fact be infinity over infinity. So you could apply L'Hopital's rule to either one of them. So over here, the limit when x is approaching 0 of the derivative of x is 1, and the derivative of tan is secant squared x, or which is equivalent to 1 plus tan squared. The derivative of tan is 1 plus tan squared, which is equal to secant squared. So at x equals to 0, that's a 1 over 1, because secant 0 is 1, or we can look at it as tan 0 is 0, and 1 plus 0 is 1. So which leads to a limit equals to 1. So this is it regarding L'Hopital's rule. Now, of course, if you wish to remember the indeterminate forms of limits, you could revisit our previous lesson on limits and indeterminate forms. However, L'Hopital's rule is one way to cancel out these two indeterminate forms, 0 over 0 or infinity over infinity. The other lesson did discuss some other techniques as well, and some other indeterminate forms as well. However, L'Hopital's rule is simply restricted to 0 over 0 or infinity over infinity, and it could also be used with 0 times infinity, because 0 times infinity can be changed to 0 over 0 or infinity over infinity, the way we saw here. However, on a quick note, for x times cotan, you could just simply apply what we did here. That's another way to do it if you were not to do it using L'Hopital's rule. You could replace cotan by cosine over sine. And then for x over sine at x equals to 0, apply this property that says that this limit, this function, or this quotient, x over sine, has a limit of 0 at x equals to 0. So we could do that since this limit is at 0. You could do it either ways anyway.